Hi, and welcome to this presentation. Today's topic is on semiconductor materials. Electronic devices such as diodes, transistors, and integrated circuits are made of semiconductive material. To understand how these devices work, we should have a basic knowledge of the structure of atoms and the interaction of atomic particles. An important concept introduced today is that of the PN junction, that is formed when two different types of semiconductive material are joined. The PN junction is fundamental to the operation of devices such as the solar cell, the diode, and certain type of transistors. All matter is composed of atoms. All atoms consist of electrons, protons, and neutrons, except normal hydrogen, which does not have a neutron. Each element in the periodic table has a unique atomic structure, and all atoms for a given element have the same number of protons. At first, the atom was thought to be a tiny indivisible sphere. Later, it was shown that the atom was not a single particle, but was made up of small, dense nucleus around which electrons orbit at great distances from the nucleus, similar to the way planets orbit the sun. Niels Bohr proposed that the electrons in an atom circle the nucleus in different orbits, similar to the way planets orbit the sun in our solar system. The Bohr model is often referred to as the planetary model. For practical purposes in electronics, the Bohr model suffices and is commonly used because it's easy to visualize. An atom is the smallest particle of an element that retains the characteristics of that element. Each of the known 118 elements has atoms that are different from the atoms of all other elements. This gives each element a unique atomic structure. According to the classical Bohr model, atoms have a planetary type of structure that consists of a central nucleus surrounded by orbiting electrons. The nucleus consists of positively charged particles called protons and uncharged particles called neutrons. The basic particles of negative charge are called electrons. Each type of atom has a certain number of electrons and protons that distinguishes it from the atoms of all other elements. For example, the simplest atom is that of hydrogen, which has one proton and one electron. As another example, the helium atom has two protons and two neutrons in the nucleus and two electrons orbiting the nucleus. All elements are arranged in the periodic table of elements in order according to their atomic number. The atomic number equals the number of protons in the nucleus, which is the same as the number of electrons in an electrically balanced atom. For example, again, hydrogen has an atomic number of 1, and helium has an atomic number of 2. In their normal state, all atoms of a given element have the same number of electrons as protons. The positive charges cancel the negative charges, and the atom has a net charge of 0. Electrons orbit the nucleus of an atom at certain distances from the nucleus. Electrons near the nucleus have less energy than those in more distant orbits. Only discrete values of electron energies exist within atomic structures. Therefore, electrons must orbit only at discrete distances from the nucleus. Each discrete distance or orbit from the nucleus corresponds to a certain energy level. In an atom, the orbits are grouped into energy levels known as shells. A given atom has a fixed number of shells. Each shell has a fixed number of electrons. The shells, that is, the energy levels, are designated 1, 2, 3, and so on, with 1 being closest to the nucleus. The Bohr model of silicon atom will be drawn and illustrated as such. So this will be the nucleus. Which has 14 protons and 14 neutrons. The silicon atom also has 3 shells. The first shell, the second shell, and the third shell. So how many electrons does each shell have? For the first shell, it has 2 electrons. The second shell has 8 electrons. So silicon, being an element with 14 as its atomic number, has 4 more electrons in its outermost shell. Okay, so there are 14 electrons. Notice that there are 14 electrons surrounding the nucleus with exactly 14 protons and usually 14 neutrons in the nucleus. The maximum number of electrons n subscript e that can exist in each shell of an atom is a fact of nature and can be calculated by the following formula. Ne is equal to 2n squared, where n is the number of the shell. And number of the shell. So using this formula, we could calculate the maximum number of electrons in the first shell, the second shell, the third shell, and so on and so forth. So for the first shell, let's say for example, Ne is equal to 2. As also illustrated by our figure. For the second shell, n is 2, so 2 squared is 4 times 2, which is also equal to 8. For the third shell, the maximum number of electrons would be 3 squared is 9 times 2, 18. Okay. So for our silicon, which only has 14 as its atomic number, will only have 4 more electrons left for its outermost shell. Electrons that are in orbit farther from the nucleus have a higher energy and are less tightly bound to the atom than those closer to the nucleus. This is because the forces of attraction between the positively charged nucleus and the negatively charged electrons decreases with increasing distance from the nucleus. Electrons with the highest energy exist in the outermost shell of an atom and are relatively loosely bound to the atom. This outermost shell is known as the valence shell. Valence shell. And electrons in this shell are called valence electrons. So for our silicon, it has 4 numbers of valence electrons. These valence electrons contribute to chemical reactions and bonding within the structure of a material and determine its electrical properties. Again, these valence electrons contribute to chemical reactions and bonding within the structure of the material and determine its electrical properties. When a valence electron gains sufficient energy from an external source, it breaks free from its atom. This is the basis for conduction in materials. There's also this concept called ionization. When an atom absorbs energy, the valence electrons can easily jump to higher energy shells. If a valence electron acquires a sufficient amount of energy, called ionization energy, it can actually escape from the outer shell and the atom's influence. The departure of a valence electron leaves a previously neutral atom with an excess of positive charge. The process of losing a valence electron is known as ionization, and the resulting positively charged atom is called a positive ion. For example, the chemical symbol for hydrogen is H. When a neutral hydrogen loses its valence electron and becomes a positive ion, it is designated H positive. The escape valence electron is called a free electron. The reverse process can occur in certain atoms when a free electron collides with the atom and is captured, releasing energy. The atom that has acquired the extra electron is called a negative ion. The ionization process is not restricted to single atoms. In many chemical reactions, a group of atoms that are bonded together can lose or acquire one or more electrons. For some non-metallic materials such as chlorine, a free electron can be captured by the neutral atom, forming a negative ion. In the case of the chlorine, the ion is more stable than the neutral atom because it has a filled outer shell. The chlorine is designated as Cl negative. In terms of their electrical properties, materials can be classified into three groups: conductors, insulators, and semiconductors. When atoms combine to form a solid, crystalline material, they arrange themselves in a symmetrical pattern. The atoms within a semiconductor crystal structure are held together by covalent bonds, which are created by the interaction of valence electrons of the atom. Silicon is a crystalline material. All materials are made up of atoms. These atoms contribute to the electrical properties of a material, including its ability to conduct electrical current. An insulator is a material that does not conduct electrical current under normal conditions. Most good insulators are compounds rather than single element materials and have very high resistivities. Valence electrons are tightly bound to the atoms. Therefore, there are very few free electrons in an insulator. Examples of insulators are rubber, plastics, glass, mica, and quartz. A conductor is a material that easily conducts electrical current. Most metals are good conductors. The best conductors are single element materials such as copper, silver, gold, and aluminum, which are characterized by atoms with only one valence electrons. Such as illustrated in the figure. These loosely bound valence electrons can become free electrons with the addition of a small amount of energy to free them from the atom. Therefore, in a conductive material, the free electrons are available to carry current. A semiconductor is a material that is between conductors and insulators in its ability to conduct electrical current. A semiconductor in its pure or intrinsic state is neither a good conductor nor a good insulator. Single-element semiconductors are antimony, arsenic, astatine, boron, polonium, tellurium, silicon, and germanium. Compound semiconductors such as gallium arsenide, indium phosphide, gallium nitride, and such are also commonly used. The single-element semiconductors are characterized by atoms with 4 valence electrons. Similar to our example earlier in the case of silicon. Also, silicon is the most commonly used semiconductor. In solid materials, interactions between atoms smear the valence shell into a band of energy levels called the valence band. Valence electrons are confined to that band. When an electron acquires enough additional energy, it can leave the valence shell, becomes a free electron, and exist in what is known as the conduction band. The difference in energy between the valence band and conduction band is called an energy gap or band gap. This is the amount of energy that a valence electron must have in order to jump from the valence band to the conduction band. Once in the conduction band, the electron is free to move throughout the material and is not tied to any given atom. The figure at the bottom right shows how each silicon atom positions itself with 4 adjacent silicon atoms to form a silicon crystal, which is a 3-dimensional symmetrical arrangement of atoms. A silicon atom with its 4 valence electrons share an electron with each of its 4 neighbors. This effectively creates 8 shared valence electrons. For each atom and produces a state of chemical stability. Also, this sharing of valence electrons produces a strong covalent bond that holds atoms together. Each valence electron is attracted equally by the 2 adjacent bonds which share it. Covalent bonding is an intrinsic silicon. Covalent bonding in an intrinsic silicon crystal is shown in the figure. An intrinsic crystal is one that has no impurities. Again, let's stress this. Covalent bonding for germanium is similar because it also has 4 valence electrons. An intrinsic or pure silicon crystal at room temperature has sufficient heat or thermal energy for some valence electrons to jump the gap from the valence band into the conduction band, thus becoming free electrons. Free electrons are also called conduction electrons. This is illustrated in the following figure. When an electron jumps to the conduction band, a vacancy is left in the valence band within the crystal. This vacancy is called a hole. For every electron raised to the conduction band by external energy, there is 1 hole left in the valence band, creating what is called an electron-hole pair. Recombination occurs when a conduction band electron loses energy and falls back into a hole in the valence band. To summarize, a piece of intrinsic silicon at room temperature has, at many instants, a number of conduction band electrons that are unattached to any atom and are essentially drifting randomly throughout the material. There is also an equal number of holes in the valence band created when these electrons jump into the conduction band. When a voltage is applied across a piece of intrinsic silicon, the thermally generated free electrons in the conduction band, which are free to move randomly in the crystal structure, are now easily attracted towards the positive end. This movement of free electrons is one type of current in a semiconductive material and is called electron current. Another type of current occurs in the valence band where the holes created by the free electrons exist. Electrons remaining in the valence band are still attached to their atoms and are not free to move randomly in the crystal structure, as are the free electrons. However, a valence electron can move in a nearby hole with little change in its energy level, thus leaving another hole where it came from. Effectively, the hole has moved from one place to another in a crystal structure. Although current in a valence band is produced by valence electrons, this is called hole current to distinguish it from electron current in the conduction band. As you can see, conduction in semiconductors is considered to be either the movement of free electrons in the conduction band or the movement of holes in the valence band, which is actually the movement of valence electrons to nearby atoms, creating hole current in the opposite direction. Since semiconductors are generally poor conductors, their conductivity can be drastically increased by the controlled addition of impurities to the intrinsic or pure semiconductive material. This process is called doping. Doping increases the number of current carriers, whether electrons or holes. The two categories of impurities are N-type and P-type. To increase the number of conduction band electrons in an intrinsic semiconductor, intrinsic silicon, pentavalent impurity atoms are added. These are atoms with 5 valence electrons such as arsenic, phosphorus, bismuth, and antimony. Each pentavalent atom forms covalent bonds with 4 adjacent silicon atoms. 4 of the antimony atoms' valence electrons are used to form the covalent bonds with silicon atoms, leaving 1 extra electron. So silicon, just 4 valence electrons, will be added with antimony valence electrons, which are 5. A chemically stable atom should have 8 valence electrons. So this will have an excess of 1 electron. This extra electron becomes a conduction electron because it is not involved in bonding. Because the pentavalent atom gives up an electron, it's often called a donor atom. The number of conduction electrons can be carefully controlled by the number of impurity atoms added to silicon. A conduction electron created by this doping process does not leave a hole in the valence band because it is in excess of the number required to fill the valence band. Since most of the current carriers are electrons, silicon, or even germanium, doped with pentavalent atoms is an N-type semiconductor. The electrons are called the majority carriers in the N-type material. Although the majority of current carriers in N-type material are electrons, there are also a few holes that are created when electron-hole pairs are thermally generated. These holes are not produced by the addition of pentavalent impurity atoms. Holes in an N-type material are called minority carriers. Similarly, to increase the number of holes in an intrinsic silicon, trivalent impurity atoms are added. These are atoms with 3 valence electrons such as boron, indium, and gallium. As illustrated, each trivalent atom, boron in this case, forms covalent bonds with 4 adjacent silicon atoms. All 3 of the boron atoms, valence electrons are used in covalent bonds. And since 4 electrons are required, a hole results when each trivalent atom is added. So this is the hole that is created by the bond between the silicon and the silicon's 4 valence electrons and the boron's 3 valence electrons. Because the trivalent atom can take an electron, it is often referred to as an acceptor atom. The number of holes can be carefully controlled by the number of trivalent impurity atoms added to the silicon. A hole created by this doping process is not accompanied by conduction or free electrons. Since most of the current carriers are holes, silicon, or even germanium, doped with trivalent atoms is called a p-type semiconductor. The holes are the majority carriers in p-type material, and although the majority of current carriers in p-type material are holes, there are also few conduction band electrons that are created when electron-hole pairs are thermally generated. These conduction band electrons are not produced by the addition of trivalent impurity atoms, and conduction band electrons in p-type material are the minority carriers. If we take then a block of silicon and dope part of it with trivalent impurity and the other part with a pentavalent impurity, a boundary called the PN junction is formed between the resulting p-type and n-type portions. The PN junction is the basis for diodes, certain transistors, solar cells, and other devices. A p-type material consists of silicon atoms and trivalent impurity atoms such as boron. The boron atom adds a hole when it bonds with a silicon atom. However, since the number of protons and the number of electrons are equal throughout the material, there is no net charge in the material, and so it is neutral. An N-type silicon material consists of silicon atoms and pentavalent impurity atoms such as antimony. As you have seen, an impurity atom releases an electron if it bonds with 4 silicon atoms. Again, since there is still an equal number of protons and electrons, including the free electrons, throughout the material, there is no net charge in the material, and so it is neutral. But if a piece of intrinsic silicon is doped so that part is N-type and the other part is P-type, a PN junction is formed at the boundary between the two regions, and a diode is created. The P region has many holes from the impurity atoms and only a few thermally generated free electrons. The N region has many free electrons from the impurity atoms and only a few thermally generated holes. The free electrons in the N region are randomly drifting in all directions. At the instant of the PN junction formation, the free electrons near the junction in the N region begin to diffuse across the junction into the P region, where they combine with holes near the junction. Before the PN junction is formed, recall that there are as many electrons as protons in the N-type material, making the material neutral in terms of net charge. The same is true for the P-type material. When the PN junction is formed, the N region loses free electrons as they diffuse across the junction. This creates a layer of positive charge near the junction. As the electrons move across the junction, the P region loses holes as electrons and holes combine. This creates a layer of negative charge near the junction. These two layers of positive and negative charge form the depletion region, as shown in the figure. The term depletion refers to the fact that the region near the PN junction is depleted of charge carriers, whether electrons or holes, due to the diffusion across the junction. Keep in mind that the depletion region is formed very quickly and is very thin compared to the N region and P region. After the initial surge of free electrons across the PN junction, the depletion region has expanded to a point where equilibrium is established and there is no further diffusion of electrons across the junction. This occurs as follows. As electrons continue to diffuse across the junction, more and more positive and negative charges are created near the junction as a depletion region is formed. A point is reached where the total negative charge in the depletion region repels any further diffusion of electrons in the P region, and the diffusion stops. In other words, the depletion region acts as a barrier to the further movement of electrons across the junction. The valence and conduction bands in an N-type material are at slightly lower energy levels than the valence and conduction bands in the P-type material. Recall, the P-type material has trivalent impurities, and the N-type material has pentavalent impurities. The trivalent impurities exert lower forces on the outer shell electrons than the pentavalent impurities. The lower forces in the P-type materials mean that the electron orbits are slightly larger and hence have greater energy than the proton orbits in the N-type material. An energy diagram for a PN junction at the instant of formation is shown in the figure. As we can see, the valence and conduction bands in the N region are at lower energy levels than those in the P region, but there is a significant amount of overlapping. The free electrons in the N region that occupy the upper part of conduction band in terms of their energy can easily diffuse across the junction and temporarily become free electrons in the lower part of the P region conduction band. After crossing the junction, the electrons quickly lose energy and fall into the holes in the P region valence band. As the diffusion continues, the depletion region begins to form and the energy levels of the N region conduction band decreases. The decrease in energy level of the conduction band in the N region is due to the loss of the higher energy electrons that have diffused across the junction of the P region. Soon, there are no electrons left in the N region conduction band with enough energy to get across the junction to the P region conduction band, as indicated by the alignment of the top of the N region conduction band and the bottom of the P region conduction band. At this point, the junction is at equilibrium and the depletion region is complete because diffusion has ceased. There is an energy gradient across the depletion region which acts as an energy hill that an n-region electron must climb to get to the p region. Notice that as the energy levels of the n-region conduction band has shifted downward, the energy level of the valence band has also shifted downward. It still takes the same amount of energy for a valence electron to become a free electron. In other words, the energy gap between the valence band the energy gap between the valence band and the conduction band remains the same.